To this point, we've talked about the different kinds of bonding that can occur between atoms. We've talked about nonpolar covalent bonds, polar covalent bonds, and ionic bonds. And all of these bonds are intramolecular bonds. These are bonds which occur between atoms within the same molecule. We can remember the prefix intra by remembering kind of a familiar word. I usually like to remember intramural sports because I think that's an easy way to remember it. And we can contrast that with something that is intermolecular. Intra means within, inter means between. And one way of remembering inter is think of intercontinental ballistic missile. So I think ICBMs, and that's how I remember inter. So if we talk about intermolecular bonds, one of the major intermolecular bonds that plays a significant role in biology is hydrogen bonding. What is hydrogen bonding? Well, we talked about positive charges that can be produced within a molecule. So if I have a partial charge within the molecule, that means that the electrons are moving towards one of the atoms, and that's giving a partial charge, partial positive charge to one atom and a partial negative charge to the other. So let's consider one partially charged molecule that you're probably pretty familiar with. Let's talk about water. So water has the molecular formula H2O, right? So this means there's 2 hydrogen atoms and 1 oxygen atom in water. Because it's a polar covalent molecule, let's draw a negative charge here and a positive charge here. The hydrogen atoms are going to spend more of the time positive than the oxygen atom, which has a higher electronegativity. So that's drawing the electrons a little bit more towards the oxygen atom than towards the hydrogen atom. Okay, so how is that going to interact then with another molecule? So let's talk about, say, another common molecule that you might be familiar with, salt. The molecular formula for table salt is NaCl, or sodium chloride. Let's see, if I tell you that chlorine is the more electronegative atom than sodium, and it's a lot more electronegative than sodium, pause for a minute and just tell me, what do you think, what kind of bond is going to form between sodium and chloride? Did you come up with ionic? Because this difference is very great between the chlorine and the sodium atoms, sodium wants to get rid of an electron and chlorine wants to add an electron. So I'm going to end up with Na plus and Cl minus, right? So how do you think this is going to interact with our water molecules? All right, so I have my water molecule here. We've learned before that positive and negative attract, right? So which of the 2 ions do you think is going to be attracted to this partially charged hydrogen? It's probably going to be this negative chlorine. And by the same token, the partially charged oxygen atom will be attracted to this positively charged sodium ion. Recall that we talked about the table salt as being salt crystals. So they come in these nice cubic kind of structures. And if you think about it, when you put salt and you sprinkle it on your food or something like that, it comes out as a nice kind of solid crystalline structure, right? But if you were to put this salt into a cup of water, it disappears. You don't see those solids anymore. It just kind of vanishes into the liquid. Once they're broken apart by these water molecules, you end up with the salt being dissolved and you end up with salt water instead. This is one of the important aspects of hydrogen bonding, is the interaction of the water molecules with ionic compounds. Okay, so let's consider how water would interact with a polar covalent molecule. Let's consider a polar covalent molecule like ammonia. the partial negative charge on the nitrogen atom and the partial positive charge on the hydrogen atom in the ammonia molecule allow it to interact with water through hydrogen bonding. This will show you how polar, covalent, and ionic, or basically charged molecules, can interact with each other. And in particular, this is also showing the importance of what's called an aqueous environment. And that's just another way of saying a water environment. It's showing the importance that aqueous environments play in the way that molecules interact with each other. And this is going to be important biologically because a lot of our biological environments are actually aqueous. So another thing that's important about hydrogen bonds is the strength. So individually, a hydrogen bond is fairly weak, but together, a lot of hydrogen bonds can actually play a very significant role in a lot of biological functions. And we'll see how this cumulative strength between multiple hydrogen bonds plays a role in some of these processes later. We've learned today a little bit about hydrogen bonding and its importance. So a hydrogen bond is a bond between a partially charged hydrogen atom and any sort of electronegative atom. Or it can be between a hydrogen atom and an anion. And it's important to note that hydrogen bonds can form both intermolecularly, so between atoms that are in different molecules, but it also can form intramolecularly as a link between atoms within the same molecule. The strength of a hydrogen bond is individually fairly weak, but we'll see how hydrogen bonds will often work together, and the cumulative strength of the hydrogen bonds is actually pretty significant and plays an important role in biology.